This is the sixth in a series of videos in which I'm developing a 40-channel logic comparator. In the previous videos I got as far as showing the initial design, and in the last video I showed the prototype bare boards. As you can see, I've now assembled a couple of boards. I've assembled a comparator board, a display board, and I've configured one of the test modules. So far I haven't fitted the timing capacitors onto the comparator board. What I'm doing at the moment is checking that all the interconnections work and that each of the inputs does what it's supposed to, and I want to do that without this being confused with any timing issues that the capacitors will produce. They're supposed to do that, but for initial testing I'm leaving them out. If you do build one of these, you won't need to do that. This is just for development testing. One of the biggest decisions when you're building one of these is what interconnections to use. There are of course a huge number of interconnections on these boards, and the connectors you use will largely depend on whether you decide to fit IC sockets to the comparator board. If you go ahead and build the board without sockets, then of course the overall depth of the test device will be much shallower, so you can use much shorter interconnections. Give you a much neater test device, but at the expense of making it hard to replace any failed ICs. That's just a matter of personal preference. I have designed the boards with slightly oversized holes for the ICs, and that's just to make it much easier to change them should you ever need to replace one if you've soldered them directly to the board. So it's a matter of personal preference, either way will work. There's also of course mounting holes for the various boards. If you're using just a single comparator board, then you can just use clicking standoffs. So I would use these heights, but you'd obviously pick the correct height for the connectors that you're using. If you're going to fit two comparator boards, then you would need to use longer screws and nuts and spacers, because obviously you can't plug a clicking standoff through from both sides. Okay, so I've got these boards assembled to this state. I have been doing some initial testing. Another choice you have here is whether you fit the test clip connector to the top or the bottom of the board. You can fit it to the top to make it more accessible. I've fitted it to the bottom. There's plenty of space. I've left a space on the comparator boards to allow for this socket. And of course what you do is you get a connector. Doesn't need to be ribbon cable, but it makes it easier if it is, and then that obviously plugs onto there. Power goes onto this connector. I'll discuss power later on. There are some decisions I had to make regarding power, and I may change it in later designs, but for now this device uses an external power source. You can clip it onto the unit under test power, but it's not automatically configured through the test module at the moment. Of course this then just plugs onto the comparator board, or comparator boards if you're using more than one. Okay, so that clips together like that. You can see it's this is about 25mm thick. If you put a second comparator board on, how big it gets will depend of course on whether again you have IC sockets fitted, but worst case you end up with a device that's about 40mm total height, or about just over 30 if you don't use IC sockets. Either way it's not particularly big, it's quite a nice compact device. For initial testing I've only built the one board. What I can do to test the lower 20 channels is of course just take this off, turn it round, plug it into the bottom 20 channels, and that will allow me to test the bottom part of the device slot. I've configured a couple of test modules, and the way these are configured is you just decide which of the IC pins are inputs, and the ones that are inputs you just put a small solder blob onto these jumpers. It's very easy and quick to do. The spacing is such that it readily accepts a solder blob, so as soon as you put solder on there it will go straight across onto both sides and give you a nice a nice neat join. The general thinking with these is that you need one of these for each type of IC you're using, and you would only need to do that if you soldered the IC direct to the board. What I've done is use a socket. So this is a 7400, and because of the common pin out thinking behind TTL devices and 4000 series devices as well, a single board with a socket on will cater for more than one type of device. So for example, this particular module with these jumpers set, without changing it other than swapping the IC, will cater for not just 7400s but also 7403s, 7408s, 7409s, 7432s, 7486 and 74132s and a few others. So you don't need a huge number of these. The only time you tend to need a unique one is if you're testing some of the larger 40 pin devices, which obviously have unique pin-out configurations. But even then there's quite a lot of commonality between different types of devices, so you don't need as many of the module cards as you might assume that you do. Once you've got it configured, this just pops into the slot at the top of the device. As I mentioned previously, there is a notch on one side to prevent you putting it in back to front, and also to stop it in the correct place once it gets down to the right level with the LEDs. So when I push this in and it comes to a stop, then it's in the right location so that each pin is directly adjacent to its indicating LED. What I'll do now is I'll just hook this up to show you some brief testing. The way I've been testing this is using a simple 40 pin ribbon cable. I've made up some plug-on jumpers here, so these are just plugged onto my test clip. These test clips, as you probably know, are quite expensive, so the way I tend to configure these is to have connectors that just push onto them. Normally I'd have these going all the way through to the connector that plugs into the test device, so there's no intermediate join. But I'm doing a lot of development testing here, so I've got these arranged so I can change them and jumper them around to do various different testing, and also to introduce faults, because I need to obviously see how this responds when there is a fault, and I don't want to have to purposefully blow up a lot of ICs to test it. Okay, so what I'll do, I'll bring in a simple test breadboard, and I'll just show you how I'm going about testing this. Okay, so this is the very simple test setup. We have the 7400 installed into the logic comparator, and this is the unit under test. Again, it's a 7400. Obviously they have to match. Normally what you would do here is just clip your test clip onto the device you're testing, and then run the unit under test and see if you get any error lines coming on. But to make it clearer, and also because I'm doing initial development testing here, I'll use discrete jumpers to connect the unit under test to the logic comparator, and then we'll see how the logic comparator responds. So as I said, I'm running the logic comparator from external power, and I'm running the unit under test from the same power source. So I'll switch that on. It's 5 volts, of course. This is all TTL stuff. And what I've got here is very simple arrangement. I'm just using one gate of the 7400. The 2 yellow jumpers are connected to the 2 inputs, and the output is connected through a resistor to an LED. And the LED will come on when the output of the gate goes low. So it's a 2 input NAND gate, so with both inputs connected to positive, the output will be low, and so the LED comes on. If I swap one of the leads around, the LED of course goes out. It will only be on when both of the inputs are high. Okay, so what we do now is we connect the matching inputs on the unit under test to the logic comparator. Now, if you recall from a previous video, I said that the layout on the connector matches the layout of the chip. So in other words, this is pin 1, pin 2, pin 3, pin 4, pin 5, etc. And this particular device, this will be pin 14. Whether this is pin 14 or pin 16 or 18 or 20 depends on the type of device, and that's why I've done this layout in this manner. It saves you having to keep looking back to the manual to see which pins to use. It's just a simple case of treating this connector layout exactly as if though you're looking down on top of the IC. Also, of course, we need to connect the power pins. One thing I didn't mention earlier was that you also need to bridge the connections for the ground and the power on the test module. So it might be on some you get more than one power line, but any other power or ground you also need to jumper those out. The connections to the device and the test is normally catered for simply by clipping on the test clip. You don't need to make the individual connections at this end. I'm just doing it here to demonstrate the device working. Okay, so the first thing I'll do is connect the power. So that will be pin 14, and that goes to pin 14. Pin 7, which is ground, 1, 2, 3, 4, 5, 6, 7, goes to ground on our unit under test. Now you notice here that we've now got some indications on the comparator, and these, if you notice, are all the outputs. If you're familiar with the 7400, we've got pin 3, pin 6, pin 8 and pin 11 are all the outputs for the 7400, and they've all illuminated, and the reason they're illuminated is because the inputs to the logic comparator don't currently match the output that we're getting from here, simply because it's not connected. I'll connect the two inputs, so that's, I'm using the D gate on this device, so that's the one we need to connect up. So that's pin 13, we'll connect that. Now of course when you jumper these out, the inputs are always going to read as no error. The light will always be out because they're always going to be the same, whatever the state of the pins on the device, simply because they're joined together. Now notice already that the LED's gone out, and that's because we've only got one of the pins connected. So I'll connect the next one. As I say, you wouldn't normally connect them pin by pin like this. You'd normally just clip on the test clip, and then finally we'll connect the output. Okay, so what we can do now is we can change the jumpers around that we're feeding to the 7400. In other words, we can effectively run the unit under test. Currently we're getting no error. If I change the jumper, we're still getting no error. I'll change the jumper again. Although the LEDs come on, we're still getting no error. However, if I now change the output from the 7400, so I'll simulate it being faulty. The easiest way to do that is for me to just remove it. Notice that the LED on the logic comparator has now come on, and that's because of course we're feeding these signals, these input signals, to the test device. So the output on the test device is doing what it's supposed to, that it's gone low, but the second input to the comparator, which is the one that we're feeding from here, is not low. It's not matching the expected output. And I should say here that there are weak pull-ups on all the pins going into the logic comparator, just to make sure there's no ambiguity in the levels on the signal. What I can do here is simulate the output doing what it's supposed to by connecting it to ground, and notice that the light on the logic comparator goes out. So now the line we're feeding into the logic comparator matches the line that's coming out of the test device. And if I again unconnect this, so bear in mind that TTL inputs are normally pulled high internally within the device whenever they're open circuit. So as you can see, it's responding nicely to the inputs. I'll connect this back to where it's supposed to be and plug the device back in. So I'm getting an error light at the moment. I'll plug this back in again. I don't advise plugging ICs in when the power's on. this should be okay. And now notice that the LED has gone back out. So in other words, the logic comparator is now saying we have only 3 errors. This gate's working fine. The other 3 gates it's saying are not working, and that's simply because they're not connected. If we were to go through and connect all the gates, then all the lights would go out, and that's essentially the way it works. If you were to clip the entire device to the logic comparator, it would only show errors now for any output pins on the unit under test IC that didn't match what the unit on the what the test device on the logic comparator is doing. In other words, if you put a known good device in here, and this device is faulty, you'll get error lights coming on, and it will tell you which particular pin is not performing the way it should. So that's essentially the way it works. I'm going through and testing every single pin one by one just to make sure that they work, and that they work within spec. Once I've done that, bear in mind this is static testing, so these are all static signals. So once I've done that, I'll fit the capacitors to the comparator board and see if it works in a dynamic fashion the way I demonstrated on the prototype board. I also do all this testing with the board reversed to test the lower 20 pins as well. But as you can see, it looks very promising so far. It's doing exactly what it's supposed to. I'll test what the maximum speed of operation is, of course, modify any component value should I need to. But it's looking like it's going to work. I'll work my way through the rest of the testing. Probably take a few days, and once that's done, I'll make a final video showing the units fully assembled and tested, and I'll then make it available on my website. But as I said, the thing to bear in mind here is that the test modules, you don't need a test module for every single IC that you want to support. If you look at 3 input devices like the 7410, the same module would do 7411, 7412, 7427s, and then when you get to the more complex devices, which is really what this device is really going to help with, then if you take, for example, the counter family, then 74160, 161, 162, 163, again they will only need a single module configuration as long as you use a socket, so you can swap the devices out. And that means that with maybe 10 or 15 of these cards, you'll have probably as many test cards as you need, except for when you need to test a particular odd device or processor or something like that. Okay, that's it for this video. Any questions, comments, please let me know.